I'm Sergio Lerner. I'm the CTO of Fairgate. Fairgate is a company that was created 2 years ago. We started working on garbled circuits, actually, doing some proof of concepts of zero-knowledge trading of vulnerabilities on chain. And it was very interesting proof of work that we did. And as soon as Robin created this new idea of BitVM, we thought that this was super interesting. We are in Fairgate, we are Bitcoiners. We've been working on many Bitcoin projects before. So for us, this was an excellent opportunity to apply our knowledge and our ideas to this new exciting thing that was happening on Bitcoin. This talk is going to be like from starters to more advanced things, but I packed everything in 45 minutes. So it's going to be like sightseeing of every protocol we did, very high level, but I just want you to know all the things that happen in 2024 and that are happening in 2025 and probably next year. So first of all, why should Bitcoin compute anything? Like, why do blockchains need to compute? I remember having this discussion with Gregory Maxwell in 2012 that he says that blockchain should not compute anything. Like moving all computation off chain was the only thing that we should do for Bitcoin. And I agree, but we need at least certain minimum amount of computation to be able to create protocols and layers on top of Bitcoin. And that minimum amount of computation, we haven't the opportunity to do this before, and I will explain why. So why we want to compute in blockchains? There are many use cases. Smart wallet is one of these use cases. Like I want to have a wallet and I want to have a better control of the spending conditions, the right limitations, or the multi-sigs, and I need really a kind of a more powerful language to write those. Of course, decentralized exchanges, we've seen automatic market makers in Ethereum and other chains. They are very, very useful to create a decentralized financial system. Decentralized organizations, outsourcing computation. Like if you really need to do a lot of computation, maybe you can outsource it and then verify it on chain. Private fair games with private strategy supporting gambling. This was my thesis on the university. I was working on peer-to-peer poker, and I wanted to have, this was 2009, and I wanted to have a cryptocurrency to let me play poker peer-to-peer. So this for me was the best use case for a blockchain. Then this is the proof of concept we did, trading responsibly vulnerabilities disclosures with Seagate proofs. And then in yellow, these are the use cases that I think are currently the most interesting. Improved Lightning Network channels. This is something that we have not yet applied all the knowledge we have from BitVM into Lightning Network. I think there will be a lot of applications. More decentralized bridge to sidechain and rollup. This is the main driver of BitVM. This is the reason why Robin created it. And the whole bandwagon of L2s that were born after this is because of this use case. And verifying the rollup state transitions. This is part of creating rollups. We need to be able to optimistically verify the state transitions. And of course, there will be new L2s based or using this technology. I'm pretty sure. For instance, I'm pretty sure that certain layers that in principle have nothing to do with BitVM will in the future integrate BitVM in some sort of another. So why compute on blockchain? Well, Vitalik came up with this definition of functional escape velocity, which is basically, he thought like, okay, what's the minimum functionality I have to put on Ethereum so that basically I can create any kind of application and I don't have to modify Ethereum ever again, right? And as we know, Ethereum is undergoing changes every single year. So Ethereum did not reach this functional escape velocity, but it's close to. And I tried to apply this definition to Bitcoin under the conditions that Bitcoin is today. That it's very hard to reach consensus on anything. So what would be this escape velocity for Bitcoin? It would be to have the minimum amount of computation in the blockchain that supports moving this Bitcoin token into layer 2s. That's the minimum amount of thing that I'm asking Bitcoin at this point, right? Everything else, we move to layer 2. But as you know, something horrible happened in 2010. There was a report of a vulnerability in Bitcoin. It was in the right shift opcode, and then Satoshi came and did this pull request, and basically he put an if, and all these opcodes, we don't know why, he chose this subset, and basically disabled them. We think that this was a temporary fix because he didn't actually remove the code that computes this opcode. He just put this guard there, preventing the opcodes to be executed. And then, very sadly, a couple of weeks afterwards, Gavin had some meetings with the CIA, and Satoshi did not like this. This is the theory. He did not like the governments to be involved in who is developing Bitcoin, and he moved away to do something else or disappear. And we are left with this horrible code that actually currently in the Bitcoin code, these opcodes are not even implemented. So it's all gone now. So we were left with this set of opcodes. The one in black are the one existing. The ones in red are the ones that were removed in 2010. And the bad thing about this opcode is that opmult was removed. And now if we want to implement opmult, we have to implement that using opadd. And it takes 3,565 bytes of Bitcoin script to implement a 32-bit multiplication. And that's the script. If you see anything, but there's a lot of drops at the end. These are all the elements of the stack that had been pushed, popped, and there are some constants in the beginning, and then a lot of adds in the middle, right? Yeah, I put it in purpose. I wanted to know if you were awake. Okay, so this is actually BitVM's code for the 32-bit multiplication instruction that was coded by Martin. Is here. So this is his work. Of course, this is not how we write the opcodes. We write in very high-level languages, and it ends up being this mess. But so what happened in 2010 is that the Bitcoin script gets split into two universes. So one universe was later called small script, and it can only operate on 32-bit words. And the other universe is called bit script that basically can operate on small or large strings of bytes, but the problem is that we cannot go back to small script. So we could eventually do, for instance, a hashing operation and hash a small 32-bit thing into a big script byte string, but then we could not do anything with that. So the hashing opcodes are very, very, they are not useful now, very low use now. The only opcode that is in the middle, it's very strange, is upsized because it gets the size of a string of bytes in big script and gives us a small script size. And there are some very interesting tricks that people have done with upsize to, for instance, apply one-time signatures to transactions using these opcodes. Very strange things. But we are super limited with this separation of words. So the history, I would say, about computing on blockchain does not start with BitVM. It's much older. It starts with probably Ripple in 2014. And the first thing that come to the mind of people is, oh, let's do off-chain trust computing, and a lot of computers do trust, in secure environments do computation and then send the response and sign it, and we will verify this on chain. Of course, this is not decentralized. No Bitcoiner will ever accept something like this. And these technologies like TEE, at least Intel TEE, has been broken over and over every year. So it's not good for us. Then we have the Bitcoin paradigm, which is non-Turing complete, space-bounded computation like Bitcoin or Litecoin, which is basically a way to measure the resource usage of computation in the case of Bitcoin using the script size. We have the method computation, which is what Rostock and Ethereum does. Basically, you do all the work on chain, but you measure the amount of resources it consumes, so you can charge for that. But then we have these new models, proof of computation integrity, where you put all the computation off chain, and by a simple and succinct proof, you can basically verify this. There are projects that are fully based on this paradigm. For instance, the Mina projects, where everything is a snark verification. The only operation you can do is, I think, is snark verification, and everything is done off chain. And then there is the paradigm of disputable computation. I would say this is the poor man's paradigm, because it's very, it's the only that is left for us to use. And it was, I think it was kicked, the first project that used it was TrueBit in Ethereum to do off-chain computation. And then came the optimistic rollups. We are fully based on this paradigm. And then BitVM come that implements or brings this paradigm to Bitcoin again. And the good thing is that because it's optimistic, when there is no challenge, the cost of this computation is very, very low. So now I'm gonna, yes, yeah, okay. But you hear me like this? Oh, okay, sorry. Yeah, much better. Okay. So now I'm gonna explain BitVM, and well, seeing you guys and girls here, I know that you know this, but let's do a recap for all the ones that will see this video later. So first, with the current paradigm on Bitcoin computing is you have a transaction and you have a program attached to this transaction. It's called, let's say, a verification program or predicate. And you have some input data, which is the witness data. And if the input data satisfies this predicate, then the transaction is accepted. And if the computation is accepted, the transaction is accepted, and then it can go on chain. So a single transaction does the computation. But there is a problem with this paradigm. It's like, let's say we want to verify a pegout from a sidechain. And let's say this sidechain is Rostock, because I have these numbers in my head. So verifying a 1,000 block pegout in Rostock will require a script that is 500 gigabytes. Okay, that's the size of the script that you would need without considering the input to just verify this pegout. But it turns out that the maximum size of a Bitcoin script is only 400, for a standard transaction, is only 400 kilobytes. So this is impossible to do. There is a technique, you probably have heard about it or use it, that is called the SNARK, Zero Knowledge Succinct Non-Interactive Arguments of Knowledge. This is a fantastic thing, mathematical thing. Growth is in Argentina this week, so maybe you can have him explain this better. So, but the basic idea is like, you could have any computation of any size, and if you do these recursive snarks, you can basically pack or create a proof of all this computation that is not only small, but very fast to verify. So essentially, you don't need, this is a data center, as long as you are able to verify a snark in a blockchain. So that actually puts a limit, a cap on the amount of computation you will ever need to do on a blockchain. Because if it's higher than this, you just compress everything and make it a snark. So that's a good thing. And that's one of the reasons why most of the teams working on BitVM are actually only focused on snarks. They do not care about anything else, because that's anything that it requires more computation should be able to be compressed into a snark. So the basic of snark is like, first you generate a verification key, then you build a proof with your input, you create a proof, and what you actually verify is the proof and the public input. And then you get either to accept or reject this proof. So let's say we do have this script that verifies a snark. Still, that takes 2 gigabytes of script. It's still too big. So we need something better. It's still too big. Okay, this value comes from the 100 pieces of BitVM2, and that adds up to I think about 2 gigabytes. Okay, so we changed the paradigm, and this is the idea of optimistic or disputable computing. So instead of having a single transaction that executes a single program, we put this evaluation into several transactions that are connected. It's not a predicate anymore. It's more of a protocol. It's an interaction between parties, and the end result is the same. The end result is that either the funds are spent or are not spent, but they require multiple transactions that are connected somehow. And so now the prover, Patrick, is also a prover. He wants to prove that the input that he's putting on the protocol is correct and satisfies this predicate. And Valerie, which previously she had a completely passive role, now she have to verify and challenge in case there is a bad input, right? A cheating attempt. So what are the technologies that enable BitVM? As I mentioned before, I think the first time the fraud proofs concept is mentioned is in Blockstream paper in 2014, because in that paper there was an opcode which is called reorg verify or something. It's actually a fraud proof system. And then we have TrueBit on Ethereum, then Optimistic on Ethereum, and then there are two developments that happened before BitVM that were foundational to this technology. Is the verification of Lamport and Winternit signatures on Bitcoin script, and this enabled the signing of arbitrary data, and then using this system the transfer of data between transactions. So a property that Bitcoin never had, which is being stateful, now there is kind of a way to bring statefulness into Bitcoin. And then when BitVM was discovered, or it evolved into multiple protocols. So there is what's called BitVM 0 or tap leaf circuit, was impractical, not implemented, but it just brought this idea. Then Robin came up with this CPU that he deprecated because he moved into BitVM 2, which is a one-round protocol, which it's finalized and it's audited, but I think it will be soon deprecated because it cannot compete against other protocols that are much cheaper, like I think Garbled Circuits based, or even BitVMX, I think, because it's very expensive to do a dispute. Then there was a first version of Garbled Circuit based protocol, which was called BitVM 3, that had the nice property that allowed circuits to be reused, but it was broken. Then there was a new proposal, more standard, I would say, more traditional in the use of JAOS standard garbling, and that is now called BitVM 3S. And then there are the two standards that we are kind of working day to day and pushing and trying to make them useful. Is the BitVMX CPU, which is kind of something similar to the original BitVM 1 CPU, although the design is different, the results are pretty similar, and an implementation of Garbled Circuits for the BitVMX platform, and that we are preparing to make public in the upcoming month. Okay. So how does this BitVM thing works? Pre-Garbled Circuit, like the standard BitVM thing. So I think we can define it very easily with this idea that for any function, for any computation we have to do, we can split that in multiple stages, like let's call them F1 to Fn. Each one of these stages has some mid state, like the snapshot of the memory at that point in time. And so any computation, we could split into this number of functions. And let's for once assume that these mid states of the computation are small and we can handle them on chain. Okay. So once we split the computation, we can actually create a series of operations that incrementally make us closer to the final result. So we start with initial conditions. We applied F1. For instance, in this case, I want to compute x plus 5 multiplied by c multiplied by 2 minus 11. And so in each stage, I can get a mid state, which is the result at that point, and advance and advance and advance until I get to the result I need. So once I have this idea of incremental computation towards a goal, then the BitVM2 method, what does is the following. It's an interactive protocol. First, Alice will put on chain all the mid states, okay, set 1 until set n. These are all the mid states of this computation. And then Bob can come and say, okay, which one of the mid states are correct from my perspective if I locally execute the same computation? And so let's say, for an example, that only set 1 is correct and the other incorrect. So Bob knows that F2 is incorrect. It's not correctly computed. So what can Bob do is go to this witness set1 and set2 and the function f, go on chain, and if the script on chain can execute f2, then basically it can prove or disprove that z1 actually it's the result of applying f2 on z1 is actually z2. Okay, so this is the only operation that we have to do on chain to make sure that nobody cheats. Z1, all the mid-state are signed by Alice. So when Bob presents these mid-states on chain, they come signed by Alice, so he cannot change them. He cannot fool the script. He only can do is bring the Z1, Z2 values that Alice signed. Probably Bob has to co-sign them to make sure that nobody modifies them in the mempool, but essentially that's the idea. Okay? The BitVMX CPU method, this is what actually BitVMX implemented first. It starts like the same, but now the search method is different. Instead of doing in one round, what Alice posts on chain is just the latest mid-state, and then Bob, okay, looks at it and says, okay, it's invalid, does not match my local computation. So Bob asks for a midpoint in this chain. Let's say the midpoint is Z2 in a transaction, and then Alice responds with Z2 signed with one-time signatures. And then this continues until we get to a point where Bob is sure that there is a function f2 that is badly computed, that is not correct. So it's the same, but instead of one round, it's multiple rounds. The other big difference is like these functions are much smaller. Like the granularity for one of these functions, in the case of BitVMX, is a RISC-V opcode, which generally takes no more than 3 kilobytes, so between 1 and 5 kilobytes. While in BitVM2, each one of these functions takes 2 to 4 megabytes. Okay, so that's where the cost of BitVM2 comes from, and that's why this is very cheap. So this is another example how we do a binary search and we get to a point where we have this mismatch. Okay, but now we have a new paradigm that competes, or it's better in certain ways than the BitVM2 and BitVMX paradigms. It's based on garbled circuits, and I'm not going to go into greater detail of how this cryptographically works, but I just want to mention on the overall how it works. Basically, what we have still an input, and we build a circuit, an encrypted circuit that receives encrypted inputs and produces encrypted outputs. And so each one of the operators will create one of these circuits, and the circuit basically checks if applying the f function, the big one, results in y when receives x as an input. And the circuit creates outputs one of two possible encrypted outputs, let's say. T for true and for false, and F for false, okay? This is something called conditional disclosure of secrets in cryptography. So the question is, how can we make use of encrypted inputs and encrypted outputs? How can we enforce that at a certain moment in the protocol, these encrypted things can become decrypted? Well, the thing is that we can make the encrypted input match a pre-image that we can verify on chain to be valid, or a signature using an adapter signature or with wish. So there is a way to map these inputs into the encrypted or garbled inputs that the circuit needs. So basically, when we need to evaluate this, it's all ready to go. So, and the output, we can just use this encrypted output inside this transaction using something that you already know probably. It's called a hash time locks. So we have a construction that is used by the Lightning Network where we have an output, and if the output receives this F that falsifies the circuit, we can do something. For instance, we can let Bob take the money or prevent the money to be taken. And in case that Bob cannot find this value F, then after some time, Alice can actually execute the transaction. So this is no. So this is all that we need on chain. It's so simple. Well, here I'm not talking about the input publication, but the output thing is very easy. Okay, these are actually approximately the results that we get. So if we had to verify everything on chain, it would take like 100 gigabytes of data. if we could somehow put a snark entirely in a Bitcoin script, it would take 2 gigabytes. BitVM2 requires approximately 4 megabytes between the mid states and the script. BitVMX CPU takes approximately 4 kilobytes for each. I think it's 4 kilobytes for each party, something like that. And Garbled Circuits, we could make it with an efficient YAO implementation with 1 ciphertext per gate. I think it's 4 kilobytes that we can get on chain. So this is incredibly efficient compared with the other technologies. What are the limitations of BitVMX in general, like any one of these systems? Well, we work on the assumption that there is one honest party on a set of n parties, of a committee of n parties. That's our basic assumption. So everything we do, we have to live with that restriction. And then generally, if we don't make something very special, there is no context for these contracts. Like they do not know the time or the block hash or anything. They are kind of isolated. So if we want, to, for instance, for a ROP, we would like to know the block hash of, the current block. We don't have that. We have to emulate that. And that's very tricky. It's difficult to do. Computation and storage costs are significant. Like if we would like to move state between these protocols, then it's costly. We need to build this preset of transactions that are connected and signed by all these committee. This is called emulated covenants. And this is something I'm going to explain more later. And at the beginning, when this was launched, it was impossible to pay to third parties from the funds that are controlled by one of these committees. Like if you had wanted to do that, you would need to do repayments, like the front and reimburse paradigm, right? You would need one operator to pay and then be reimbursed. We now have at least 2 ways of doing this without this paradigm. The 2 protocols that we published this year, and we are going to publish a new protocol, hopefully also this year, that is based on one of N's security covenants directly on Bitcoin. So why is important this one of N security property? Because before this, we had these federations, like the Liquid Federation that controls the bridge. And the problem with this federation is like they cannot grow. They cannot be permissionless, because as soon as there is a permissionless way of growing it, then anyone can cyber attack the system, take control of it, and steal all the funds. So we had these 2 kind of different paradigms: the T of N federated paradigm and the one of infinite paradigm that only existed on Ethereum, right? Where any user could challenge something. Well, BitVM brings us this new paradigm of one of N that is kind of sitting in the middle. So it's not as good as one of infinite, but it's not as bad as T of N. And the good thing is that it gives us back this permissionless grow. Okay, so let's say I'm an honest party and I belong to one of these committees. I don't care about this committee growing and growing and growing, because as far as I'm part of the committee, I'm secure because I can challenge anything. So I think this property is fantastic, and for one of the bridges that we've built from Fairgate, the Rostock Union Bridge, we have this committee to be able to grow and shrink at different stages, and it can continue to do so. So we don't have any problem to make it permissionless. So this is mostly what happened in 2024 and the beginning of 2025. But I'm going to go further. I'm going to try to explain you what's next and what happened in the second half of this year. So first of all, there is a lot of investment and ideas and projects that were kicked off because of this innovation. This was taken from the Messari report from this year. You can see that there are several L2s that are the ones that are circular. All of them are using BitVM in some way. So yeah, we have Citria, Building on Bob, BitLayer, Goat Network, Fiamma, Alpen, and Rostock, all working in different implementations or using the BitVM2 implementation. So this is super exciting. There is also the BitVM Alliance, which are several companies that join forces to push for certain standards. And the two standards that are now being developed by this joint effort is BitVM2, which basically I think it's finished, and BitVM3S, which is the garbled circuit implementation. And this is an interesting example of collaboration, but they focus only on the verification technology, not the bridges. The bridges are very different. Like if you want to build a bridge, you can just take the verification technology, but you have to build everything else, like all the components that surround the bridge. Maybe in weighting the code, this could be like 30% of the code, but 70% of the code is just the bridging technology that goes around it. And well, these different actors have different implementations of that. So kind of each one took different design and different roads. We, Fairgate, and also studied with Rostock Labs, we tried to create an open source platform where we could plug all the verification technologies, our own verification technologies, and make this open source so that we don't have this different implementation, or at least everyone is using the same system to build bridges. So we don't have completely separate code bases. Okay, so that's our aim. That's what we've been working for. And so we also created kind of alliance to push for this platform. Started with Rostock Lab, Fairgate, and Input Output. And currently we are supporting three main goals, three main projects. The BitVMX CPU, we are continue supporting and improving it. The BitVM platform, which is this thing that plugs in a lot of components and allows you to create protocols and bridges, like general purpose multi-party protocols on Bitcoin and bridges. And then the garbled circuit implementation. And I hope we soon have more verification technology from some of the people here that are working on improvements. So this is how the current BitVMX platform looks like. So you have the RISC-V CPU, which is, you can use it today. It allows you to compile RISC-V programs and verify them on Bitcoin, but then you have a lot more components that are built and allows you to do other stuff. The protocol builder allows you to define in an abstract way the whole protocol, the fraud proof and everything that needs to happen, and it just orchestrates everything for you. The transaction monitor obviously monitors what's happening on Bitcoin. The Bitcoin coordinator allows you to do this fee bumping automatically, so you don't have to pay attention to that. It's done for you. The Bitcoin indexer takes some indexes the Bitcoin blockchain to be able to use it. Key manager allows you to store private keys, not only Schnorr, but also one-time keys in a secure way. Storage backend backs up the whole state of the protocol. So if your server goes down, when it goes up, it has everything it needs to keep going. This RISC-0 adapter allows you to use RISC-0 as the program that you want to run. So you basically have everything set up so that you compile on RISC-0 and verify on Bitcoin using the SNARK verifier. And then you have message broker and a Bitcoin wallet and more components. So this is all you get for free when you start working on BitVMX. And this is the components that we want to build from now on. These are, all things are new. Each one of these has a paper that we published with different collaborations. So I'm gonna just explain a little bit about each one. So we have an improved CPU with like better trade-offs that we want to launch. We have our own garbled circuits approach. We published the Flex paper, which allows you to have on-demand security bonds. I will explain more about this. We published the TUP paper, which allows you to in bridges to let the end user receive the funds directly from the sidechain without going through this fronting system. We have the SP protocols that allow you to verify STARKs directly on Bitcoin without going through SNARKs. Many of the Bitcoiners would not want to have this trusted setup, so they would prefer to verify SNARKs fully on Bitcoin without going through this technology that may not be quantum resistant. Then we have the covenants paper. I think this would be very useful for many use cases that we are working on and hopefully publishing this year. The battle protocol is a protocol we publish that allows you to have committees up to 1,000 of parties. And that's interesting. The WISH is a system for shrinking the size of inputs of garbled circuits and BitVMX, div-snark, and a specific type of snark you probably heard of, and one-time signed payment channels. And this was a latest paper we do. So we show how to apply one-time signatures to payment channels. And I think there's a lot of things to research there. Okay, so let's focus on this flex paper. And I will explain a little bit about this. I chose 3 of these kind of randomly, three that I like to explain better. So the problem of all these protocols is the security bonds. Like all the decentralization of these protocols is very much related to how it handles security bonds. So the role of security bonds on Bitcoin protocols. This is for offsetting expected gains for a cheater in a probabilistic repeatable game. Like you have to make sure that an attacker loses money probabilistically if he tries to cheat, right? And so you need the attacker or anyone that has potentially can attack the protocol to put the security bonds so that the math makes him lose money instead of make attack attempts for free, right? And then you have to reimburse all the participants that involve in dispute, that participate in dispute, because they are honest, they are trying to defend the protocol. This cannot be costly to them, especially in BitVM2, where a dispute could go, I don't know, from 20 grand to 100 grand, depending on the congestion of the network, right? And also you have to discourage griefing attacks, like malicious parties that just want to bother and maybe delay or spam or prevent things from happening. So that's why we need security bonds. But there is a cost of security bonds, a financial cost. It's the opportunity cost. Like if I put a lot of money in security bonds, then this money could be put somewhere else, like getting some yield of some kind, right? And then there's a compound cost, because I could reuse that to get more money. And this will only increase with more Bitcoin layer 2 that gives you yield. So every time a new Bitcoin layer 2 advertises that it's gonna give you a yield, it's competing with putting your security bonds on this protocol. So we need the security bonds in some way or another. It's simpler to use static security bonds. Of course, the protocols get simpler, but the real reason we use static security bonds is because we need these covenants that we built with this one-of-n security. We need to know the UTXOs, the ID of the transaction that deposit the money. That's the hard truth. That's why we cannot live away we cannot handle dynamic security bonds, because we need the transaction IDs of these transactions that are funding the security bonds. Well, so this is same as I said before. What's wrong with static security bonds? It affects duration of the protocol, scalability. Like if you have more participants, then the security bonds can get quadratic on the number of participants, which is very bad because if you have more collateral, then it's less efficient. And basically it affects decentralization. The higher the security bond, the hardest would be for you to find a federation, an operator on this federation that wants to participate. Actually, I was reading some time ago that one of these teams, I don't remember which one, was trying to get some companies to join the federation, and it couldn't, because the initial cost was too high that it was very hard for them to get them to participate. So this is the solution that Flex provides. You can read everything on the paper, but basically it allows you to do on-demand security bonds, okay? And that opens a lot of possibilities. So it's built on BitVMX Garbled Circuits or any other. You could use it for any other Garbled Circuits implementation, not only BitVMX, but we are trying to implement this for BitVMX. It uses 2 Garbled Circuits per dispute, not just one. It requires 2, but the cost is low. And then with this method, you can basically fund the dispute when the dispute happens, only when it's needed, right? And this, for instance, in the case of a breach, only if there is a dispute on a peg out, you would need to put the security bond, okay? So basically the problem is now solved. Okay, another thing, covenants. This has a long history in Bitcoin, right? So what are covenants? Covenants enable the setting constraints on transaction outputs, okay, on how the transactions that spend funds, you want to put some constraints on which transaction can actually spend the funds. And this materially improves Bitcoin scalability and security. There are many, many use cases being discussed from 2012 that require covenants, such as Turing complete smart contracts, vaults with revocation keys. Like, this improves substantially the security. Like, if I could have a revocation key that allows me to, if I see that my funds are being moved, I can revoke them and take them back to a cold storage address, etc. Obviously, more decentralized L2 bridges and decentralized organizations on Bitcoin that were impossible because the lack of covenants. So there was many proposals to bring covenants on Bitcoin. All of them kind of failed, and we don't know if we ever will have covenants on Bitcoin because of the difficulty to reach consensus. So what have we done to overcome this problem, specifically for bridges, because bridges is the main use case. So we can think, okay, let's do an N of M multisig, okay? So basically, let's say we have a lot of operators and they want to pay to a third party, then all of them sign a multi-signature or an aggregated signature and then pay. Okay, that's fantastic, very easy. But in the case that one of these parties is not a variable, then it breaks completely, right? Because you don't have that signature, you cannot pay, okay? So it breaks. You need something different. Optimistically, it works, but in a very potential case where one participant loses the private key or just everything breaks. So what we have done to solve this in all these BitVM implementations? Well, we have this fronting reimbursement paradigm where basically there is a setup where we create transactions where we can pay to each one of these operators, okay, under certain constraints. And then when there is the time for reimbursement, well, there is one operator who will front the funds to the end user, and then it will provide a proof on chain somehow, and if that proves it's correct, he will be reimbursed from the protocol. Okay. The problem with this is the capital efficiency. This is costly, and it puts a constraint, a bottleneck on the exit of funds from L2. And if there is a constraint, there could be a bottleneck and a run to the currency. Let's say everyone wants to go out at the same time, and there are not enough liquidity, then you could have a depeg, and which would kind of destroy this L2. So the covenant paradigm is very simple, and this is what we are working on. It's basically a system where the UTXO can go directly to the end user, even if there are some participants that are not present. Okay, under the security assumption that one of N is honest. So same security assumption, we get this done. Well, this enables a lot of things. Okay, so this is the way it works, or at least the properties. So there is a committee C of N parties that control one UTXO, that they can dynamically build and execute a transaction T that consumes this UTXO, so that this T transaction can have any specific qualities or properties that you want, the destination address, the amount, etc. You can prove that withdrawal is correct, like with a snark, with a dispute system as before. And if this T can have a change output that returns part of the fund to the same committee, that's possible. And in the case that there is a subset of these parties that is a variable, then you still can execute T. That's the ninth property. And it's secure if one of these N members of the committee are honest. So the properties that we would want. And the use case that we expect this will provide is, first, of course, the layer 2s with no fronting and reimbursement paradigm. I think this competes with TOOP. It's kind of different. At least this is more on the Bitcoin side. So you could actually apply this to any protocol without re-engineering everything, while TOOP really requires a complete redesign of how the protocol works. So I think this will be good. And I think they will enable Bitcoin DAOs for the first time, because you can have all the funds of your organization or your DAO in a single UTXO. And if you use recursive covenants, you could pay to a third party based on a proof of something that it is correct. And the change could go again to the same committee and with the same restrictions. So basically, you get all the functionality. And so we are working on recursive covenants. Okay, and last but not least, I don't know how much time I have, but I will. It's the battle protocol. So the BitVMX battle protocol basically tries to solve the problem where most of these protocols that we've talked about cannot grow more than a small n. Like they need to generate this transaction DAG, this emulated governance of huge graph of transactions for each peg-in, for parallel peg-outs, for, there's a lot of explosions in the number of signatures and transactions. And so generally, the number of signatures each party has to sign is in the order of n cubed. And also, the amount of security bonds generally it's in the order of n squared for the number of parties. And of course, this restricts the number of parties and restricts the decentralization of the protocol. So the higher the n, the more decentralized the protocol is, right? So we want to have higher values, higher number of protocol members, either operating as operators like the fronting funds or as watchtowers, making sure that node operators behave correctly. So there are two problems when you grow the number of participants. First, what could happen if all the watchtowers challenge your honest attempt to withdraw funds, to be reimbursed? Let's say there are hundreds of these watchtowers. You may not have the capital to fight with them all at the same time. So you are cyber attack and you lose, okay? And if you lose everything, generally. The other thing can also happen. Let's say you are a watchtower and now a lot of operators cyber attack, they at the same time try to withdraw the funds or get reimbursed from the funds, and you want to fight against all of them, but you cannot put all the security bonds at the same time because you don't have that money, so you lose again. So this is how we break. And in the battle paper, you can see that there is a solution to this problem, and it can be implemented in Bitcoin that allows you to fight any number of watchtowers or participants within log n stages, log n rounds. That's very good. It requires a constant amount of security bonds, no matter how many watchtowers or operators you want to fight against. It's based on the Flex protocol that I mentioned before and in Garbled Circuits. Each party only needs to perform n squared number of signatures, which kind of better, and also store n squared number of data pieces like transactions, signatures. So that's good. And it's practical for n to be 1,000. Okay, so this makes it practical for 1,000 operators or watchtowers. Of course, generally, most of these operators or watchtowers will engage in the protocol because they want to have certain return. So I don't think we will ever reach a point where we need 1,000 operators or watchtowers, but this makes it possible. Okay, and the main constraint is the Garbled Circuit table size. So the more the participant, the more tables you have to store. So, but not regarding the other things. So I think this is also very promising for DAOs, big DAOs, large DAOs. And to give you a glimpse of how it works, it creates two phases. In the first phase, if you have many assertions that compete each other, that are in conflict, let's say there are 100 operators and each one of them says that the funds should be withdrawn or given to them, then in the first phase, you have a tournament where they all compete between each other in a logarithm number of rounds. You get just one winner. And after that, if that winner is still dishonest, then you have a challenge phase in that in logarithm number of rounds, the watchtowers can fight this assertion and win. Okay, so two times log n, you have all the protocols solved. Okay, this is the basic idea. So what are the possible applications we foresee with all these building blocks coded and included in the platform? I see better bridges, decentralized exchanges, vaults, lending and borrowing systems, payment channels, maybe channel factories, all these protocols, and I see the beginning of protocol of Bitcoin DAOs coming into appearing from using these technologies. And yeah, I think this is all I wanted to transmit to you today. We are from the beginning, from more than I think it's a year and a half ago, we started trying to collect all these new pieces of news that are happening in this ecosystem from all the participants and put everything in this newsletter, which is a Fairgate's Computing on Bitcoin newsletter. I invite you to join, to receive it, and get an update of all the things that are happening, which is quite a lot. Okay, that's all I wanted to say. I don't know if there's questions.
What are the liveness assumptions for the covenant, the second one you described?
Yeah, the liveness assumptions are the same as all these one-of-n protocols. Like, if there is a challenge window where if there is a participant that does not show up, then it's excluded and the protocol continues.
But you can make a transaction that can spend to an unknown person at the time of the setup of everything, right? Like who has to be live to construct the transaction?
Yeah, so in the moment you need to actually build the transaction, which is not during setup, but at a later time. There is one operator that has the responsibility to build the transaction and provide this input, I would say the data of this transaction. That could be just the destination address, or could be more data, like certain parameters. And then the others have to agree with that. That's the dynamic of the protocol. But if there are participants that do not agree, or they are not live, then they are excluded. Okay? So it's very easy to, it's what you would expect from it.
You're not just running the transaction building an MPC, are you? Or that's kind of what I'm getting at.
Transaction,
when you build the transaction.
Yes.
You're not doing that in an MPC
amongst. No. Okay. To do that on NPC will force you to have everyone live, right? So that does not work. So that's the idea is like you have to support. Yeah.
So if one guy builds the transaction and then I assume the user has to agree to it, is it incumbent upon the user to make sure that there's enough outputs there and that he's like, okay, 10 people were live, that's good enough for me? Is that kind of how they envisioned?
Well, that was happened with Tube. In Tube, you have the end user that makes a decision based on the subset. In this case, there is a challenge window, and if during that time, the only one, like everyone is off, then the transaction, it's executed with the operator that is supposedly honest. Let's say the worst case will be the operator is dishonest, nobody shows up, nobody challenges, and then the operator could actually execute any transaction. Okay, so that's the worst case.
But if the operator constructs the transaction that pays out to the challengers,
yes.
What if he doesn't put any in there? What if he only pays out to himself? And then challenge him.
What happened? I think I'm not sure I understood, but there is a proof. Well, anything that the operator wants to do must come with a snark proof or any kind of proof. Let's say the L2 commands a withdrawal because some tokens have been burned in the L2, and then there is a proof that is a snark that is being put on chain. So as long as nobody challenged that proof, then it can go. Like if the proof is invalid, obviously the operator can take the funds. Okay, but should be the same as BitVM2 or BitVM3. Like we assume that the watchtower will challenge. And if not, they can lose their security deposits.
But in those paradigms, we assume that there's a liveness assumption on them that says they have to be online to construct the challenge transaction.
Yes.
To construct the initial transaction that gets broadcasted if there's a challenge, and they all have to make sure that they have an output in that transaction or an input.
Yeah, you want to answer that?
So the idea is that there is a predicate that is predefined that evaluates the transaction, and at the payout time, at the time of executing the covenant, and that predicate evaluates whatever subset of operators are available at the time are proposing. If there is at that time a single honest operator, he can prevent the rest from trying to push a transaction that doesn't accept under this predicate. That is the idea. Anyway, this was like a preview. This is not the formal presentation. We wanted to, we are trying to get some interest on this. We think it's really interesting, but the details are not. We are not publishing the details yet. We are teasing everybody. Yeah, sorry about that.
So the two other papers are published. I just wanted to give you a glimpse of what we are working right now and publishing in a couple of 1 or 2 months. It's not something we 10 years. Just we are working on the details, right? But I just wanted to tell you that this is going to get more powerful, and I'm sure that someone will find better ways to improve this, and we will try to integrate everything new, everything better into the BitVMX platform.
And just building off of it, like more basic questions on, like, is your intuition that this will just replace TOOP entirely? Because it sounds like there's a lot of kind of overlap here. Yeah, I mean, if you already have a protocol design, then this is much easier to implement because it's more on the Bitcoin side. I would say that TOOP still has kind of the benefit that the end user has a time window where he can actually do nothing and wait forever until the operators are all giving him the share of the private key. So here there's not such a thing. Like you fix a time window where the operators have to show up and challenge, but that is fixed. The end user has no control on that. So I think that in that regard, TOOP is better. But I think from the complexity perspective of the protocol, this is better because this is
TOOP doesn't require garbled circuits, right? It's simpler in terms of the managing the costs.
But this would require garbled circuits.
Yeah. This is built on garbled circuits. Yeah, this is built on top. But there are kind of close relatives. They are where we arrive at TOOP and this thing can have similar problems. So they're closer. Yeah, closer.
You expect like you alluded to this, the integration of like existing bridges would be able to easily append this on, or is there like a mass change to the transaction graph in the bridge itself?
Well, it depends which platform. If you are using BitVMX, it's just a matter of using. There is a protocol builder component that allows you to malleate these designs very easily. But I don't know other platform. Maybe you have to design them from scratch. Like it would be easier from BitVMX because you have all the things already kind of connected in some way. I don't know other platforms. I think we will try to make this flexible and allow the easy transitions, right? Like in the end, it's just one event from a sidechain or rollup you want to verify. So all the things that happen in the L2 would be the same. Basically, you have to change the Bitcoin side. And we have 2 schemes that will be put in the first paper. One for recursive covenant and that has some other properties, and one for non-recursive covenant. So we have also different kind of trade-offs. When we finish with all these DevConnect and the LabitCon thing, we will start working again on the papers. I think 1 month, 2 months will be the what we expect.